Hello, from my last video discussion, I ended with this formula for the induced voltage of a DC generator. So basically, uh, I just explained what how to interpret this formula. You have the voltage at the armature as equal to your number of poles, total flux, RPM, revolutions per minute. Then you have the total number of conductors divided by 60 and the number of parallel paths. Of course, if your speed is given as revolutions per second, you will no longer be needing this constant 60 at the denominator. But yeah, if you're lost with this equation, I suggest you go back to that previous video lecture. Now for this lecture, I'll be discussing the different types of generator according to excitation. Yeah. So the most obvious one is your separate. Well, it's not very obvious, but I guess the simplest one is your separately excited generator. This is the simplest one because this is the one closest to your permanent magnet DC generator. The idea of a separately excited DC generator is that you have the field lang. Oops. Ay, sorry. Ano ba to? Nope. Yeah. You have the field separate from the armature electrical circuit. So because this field is separate from the armature, the excitation of this, which is dependent of your voltage, field voltage, because this is an electromagnet, this field voltage is separate from your terminal voltage, and that simplifies things because a separate field may make your the magnetic fields of the machine practically constant regardless of the loading. So because what actually happens to your DC generator is at different loading, from 0% to 100% loading, your terminal voltage may differ, as I have discussed in the formula for voltage regulation. Now, since your field is separate from the terminal voltage, then this field is practically constant. That's basically it. So you have a separately excited field separate from your terminal voltage. Therefore, your EA, which is this formula, will be directly proportional to your NRPM, since flux is practically constant. Of course, your P, your Z, your 60A are constants because they are constants of the machine. They are constants due to the construction of the machine, as shown in this formula. So you have E as equal to a certain constant K times flux and then speed of rotation. But since flux is practically constant on a separately excited DC machine, then you can say that EA is directly proportional to to the speed of rotation. Now that's one of the simplest ones. Your torque is directly proportional to the current at the armature. That is from this formula. Yeah, this one. Now, if you look at the working equations for a separately excited generator, you have the line currents going to the load, or the load current equal to the armature current. You have the voltage at the terminals equal to your armature voltage less the voltage drop at the armature, or your circuit resistance. And then you have the field current equal to the voltage at the fields divided by the resistance of the field. So that's separately excited DC generator is very, very simple. Now, a more complicated one is your shunt and your series DC generators. Okay. Now, the idea of the shunt and the series DC generators is that your field is no longer separated from the armature coil. Your field coil is no longer separated from the armature coil. For a shunt DC generator, the field coil is shunted on the armature. It's connected in parallel to the armature. Thus, your voltage terminal will also be the voltage of the field. Now, as I have said before, your voltage at the terminal may differ depending on the loading of the machine. Therefore, at different loadings, you may have a different voltage terminal, thus a different voltage at the field. And because of the different voltage at the field, therefore you always have a varying IF, and a varying IF will produce a varying flux, and that will cause a varying EA, because your armature voltage is dependent on the magnetic field flux. However, you want to have a constant voltage for a generator, and because of that, you want to have a good voltage regulation. So you want to, at least if there is a variation in the voltages at different loadings, you want that variation to be very, very small, such that you may want to make this voltage terminal constant. And if you make this constant, therefore that makes your field flux practically constant regardless of loading. And then you have the same relationship for EA and NM, the same for torque and armature current. Now, what's interesting here, as opposed to your separately excited DC generator, is that your working equations are a bit challenging. The field current is no longer equivalent to the load current. The load current is no longer equivalent to the armature current. Your load current is actually equal to your armature current less the field, or your armature current is equal to your field plus your load. Now, your terminal voltage, it is still equal to your armature voltage less the voltage drop at the RA. And your field current is equal to, well, it's still equal to VF over RF, but your VF now is equal to VT. So that's why you have this formula. Now, you may want to take note of this residual magnetism, because this residual magnetism assists in the voltage buildup. The simplest explanation for that would be the startup of DC shunt DC generators. You see, when you start from a cold start, or from a yeah, when you start from a cold start, so your DC generator, your prime mover is not yet running, therefore you actually don't have a voltage here. And if you don't have a voltage here when the DC generator is off, if this DC generator is off or cold start, you don't have a voltage here, and if you don't have a voltage here, therefore you don't have a current here. And since you don't have a current here, you can't make an EA, an induced voltage at the armature, because you don't have a current, therefore you don't have a magnetic field. Now, when starting a DC shunt generator, you actually start with separate excitation just to have a small voltage here, and then you build on that voltage, because the presence of a small voltage here will cause presence of a small magnetic field here. Now that magnetic field will have a residual magnetism from the previous voltage, therefore it is quite stronger than then you'll build up a bit more voltage here, therefore producing a bit more voltage here, producing a bit more magnetic field here, producing a bit more voltage here, and so on and so forth until you reach a steady state value of the nominal voltage of the terminals of the DC generator. So that's basically this explanation statement here. Now the last one, well, it's not the last one, but yeah, the other one would be your series DC generator. So the idea of the series DC generator is that your field coil is in series to your armature coil. So because of this, you have an armature current that is equal to your field current, which is also your load current or line current. Now, the terminal voltage, as opposed to your separately excited and shunt generator, would be your induced voltage times armature current. Sorry, less armature voltage drop and field voltage drop. Now what happens here is that your field flux is highly variable. It's dependent on the loading. It's highly dependent on the loading. Well, of course, it's not, as opposed to your shunt generator, it's no longer reliant on your terminal voltage. It's more reliant on your load current, and it's highly variable depending on the loading. Of course, if you are not loaded, therefore you don't have a load current, and without a load current, therefore you don't have a field current producing no magnetic field. So you want this series DC generator to be loaded, and your magnetic field is directly proportional to your armature current. Now your torque is directly proportional to Ia squared. So the idea of this is that your torque at the armature, as opposed to the one before, yes, this one, your torque at the armature is actually, your torque induced is directly proportional to your armature current and magnetic flux at the magnetic field. But since the magnetic field is also dependent on Ia, that makes this equation dependent on Ia and Ia, or Ia squared. So I guess what the interpretation for that is that your torque is dependent by the square of the armature voltage, not just the square of the armature current, not just the armature current. um, yeah, that's your separately excited, your shunt, and your series. Now the other two would be a combination of series and shunt. We have long shunt and short shunt. Well, long shunt is when you have a series coil, a series field, series to the armature, and then the series combination of that is in parallel to another field. Well, I guess the advantage of this is that you have two sources of magnetic fields. Usually I think this is more common. This is easier to do. You have a shunt DC generator, and then to you have a shunt DC generator, and then to reinforce the magnetic field, you add another series field. So you have a shunt DC generator, a shunt field, a field in parallel to the armature, and then the parallel combination of that is in series to a series field. But these are basically modifications of your series and shunt DC generator to improve the magnetic field and the voltage output. Yeah. You may also want to take note of the working equations here. You have, for a long shunt, I guess the more important one is that your net MMF is your MMF on the shunt field, and your MMF on the series field minus your armature reaction. So yeah, that's it. I guess I'll upload another video for the examples of this, but for the different types of DC generators, well, yeah, that's it. So yeah, see you soon.